Okay. So, what we're doing is number 22, homework number 11. And this is wrong because it was mistranscribed. And nobody seemed to catch it. Does this look right to everybody? I should have asked that first. If it looks wrong, speak up. So now we want to compare outputs. A is different from B, C, D, and E. We seem to have started A, B, C, D, E, F, G. There we go. Well, another blemish. B, C, D, E, F, G. H is supposed to be here. We better do it again. B, C, D, E, F, G, H. A, B, C, D, E, F, G. There. Okay. A is different from B, C, D, and E. A is different from G. B is different from F and H. C is different from F and H. D is different from F and H. F is different from G. E is different from F and H. And G is different from H. Okay. Is A equal to F? So A is equal to F if A equals B. But A does not equal B, so this gets an X. Does A equal H? A equals H if A equals H, and that's true if E equals G. Here's E, there's G. So this depends on EG. Let's look at EG. E equals G if D equals D, and if A equals H. A equals H. So this depends on EG, that depends on AH. So now I have A is equivalent to H, and E is equivalent to G. And so I get a couple of check marks. Let's keep going. B and C. B and C are good if B is equal to C and if F is equal to H. So that depends on FH. F is equal to H if B is equal to H, but it's not. Therefore, this gets an X and that gets an X. B is equal to D if C is equal to E. And B is equal to D if F equals F. Does C equal E? C and E. C is equal to E if B equals D. And if A is equal to H. A does equal H. Therefore, CE and BD are both equivalencies. And so now I have B is equal to D, equivalent, and C is equal to D. Now let's see where we're going with this. Geez, we're getting different results, aren't we? Very different. Let's look at B and E. B is equal to E if C equals D, and they are, and if A equals H, and they are. So now I have B is equal to E. B equals E, right? So B equals E. That gives me another equivalency. Now let's do another one. B is equal to G. B equals G if C equals D, and it does. And it's also B equals G if F is equal to H, but it doesn't. So it gets an X. C equals E if B equals D, and it does. And if F equals A, and it doesn't. So that gets an X. C equals G if B equals D, and it does. And also C equals G if H equals H, right? So I'm asking the question, does C equal G? C equal G. Well, B equals D, H equals H, so indeed C must equal G. And so now I've got another equivalency. And in fact, if E equals C and G equals E, then C equals G, no doubt, just from the transitive property. And so now I've got two more to go. Does D equal E? D equals E if E equals D. That's good. And if A equals F. Does A equal F? No, it does not. Get an X. Does D equal G? D equals G if E equals D. D equals G if E equals D. Does E equal D? Here's E. Here's D. E does not equal D, so this goes out. So now, if you see G over here at the bottom, anywhere you write G, you can cross it out and write in B. Anywhere you see E, you can cross it out and write in B. Anywhere you see D, you can cross it out and write in B. And that leaves us with H. Anywhere you see H, you can cross it out and write in A. And now you have A, B, F. No, A, B, C, F. So this is all that's left. A, B, C, and F. Now, let's see how we made out. A, B, C, and F. Yes, that is the answer. A, B, C, F, and then the other one says A, C, C, F. A, B. You can write A, B, or A, C, I suppose. So I think we've got a good answer in here. There may be a blemish, but it's pretty close. So that gives you an approach to the problem, which I think gives us a nice answer. Let's go to the next question, because this was a long question. Can we do number 23? Didn't we do number 23 last time? I'm just going to check my notes because I thought we did this already. Yeah, as a matter of fact, this was done. Number 22 was done last time as well, I think. And when I go back, let's just check. You know, if you guys are reviewing the recordings, yeah, we did number 21 last time as well. So that was done. So, you know, this stuff has been recorded. We did number 20 last time, and we also did number 17 last time. So if you're able to watch the recordings, you should be able to see these things have been done before. I think there's no sense doing them twice. But in any case, I don't know that we did number 23 before. And someone writes, doesn't H not equal F when comparing C and D? Let's go back. H does not equal F. So when you compare C and D, H does not equal F. That's true. H does not equal F. Did we write that A was equal to H? A is equal to H if A equals H, and if E equals G. Does E equal G? Yes. Oh, okay. That's all right. I was going back going, did I make another mistake? It's possible. I'm going to go to number 23. Number 23, this is another long one. We got a present state, a next state, and an output. And in the present state, we're going to have choices x equals 0 or x equals 1, x equals 0 or x equals 1. And the present state is listed as A, B, C, D, E, F, G, H. So this is number 23. A, B, C, D, E, F, G, H. And now he says, oh boy, H, C, C, D, H, B, F, H, C, F, F, G, C, F, F, G, G, C, A, C. And then for our output we write, let me make sure I got this right. 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, and then it says 1, 0, 1, 0. Did I do that right? Look all right to everybody? Because if you make a mistake at this point, all the rest gets kind of called to question, or is in general wrong, depending on your point of view. So let's go through this. B, C, D, E, F, G, H. A, B, C, D, E, F, G. Now, let's see where the outputs are different. It looks like A is different from everything except for G and H. Oops. Got carried away there, sorry. B is different from everything except for E. C is different from E, G, and H. D is different from everything except for E, G, and H. E is different from F, G, and H. F is different from G and H. And G, it could be the same as H. We don't know. So that's what we're left with now. That eliminated a lot. Let's take a look at A and G. A and G are the same if H is equal to G and if C equals C. So let's just look at H and G. Is H equal to G? We don't know. So H is equal to G if A is equal to G. So we have a circular dependency, and if C is equal to C. So if H is equal to G, A is equal to H if H is equal to G, and H is equal to G if A is equal to G. Let's do it again. A equals G if H equals G. H equals G if A equals G. So I say they're all equal. Let's forget about the colors for now. So I have A is equivalent to G, and G is equivalent to H. Let's look at A and H. A and H are good if A is equal to H and C is equal to C. So now I have A is equivalent to H, and yes, indeed, that is true because of this. Now let's take a look at B and E. B is equivalent to E if C is equal to C, and it is, and if D is equal to F, and we don't know. So what about D and F? D is equal to F if F equals F, and that's good. And if H equals G, it does. So D equals F, and C equals D. So I have C equivalent to D equivalent to F. That's pretty good. Got a lot of equivalencies now. Let's take a look at B and E. B is equal to E if C equals C. That's pretty good. And if D equals F. D equals F. It does. So now I have B equals E. Right? B equals E if C equals C and D equals F. So B equals E. C equals F if H equals F. It does not. And now I've got my equivalencies right in through here. I can take out H, and anywhere I see H I can write in A. I can take out G, and anywhere I see G I can write in A. I can take out F, and anywhere I see F I can write in C. I can take out E, and anywhere I see E I can write in B. I can take out D, and anywhere I see D I can write in C. That's a lot of reduction, isn't it? I'm down to ABC. Let's see if that's an answer. This is question 23. Question 23 says the answer is ABCD. Were we incorrect in removing D? We somehow said that C was equal to D. And C is equal to D if F is equal to H, but f is not equal to h. I don't know how we got that. F is not equal to h. So that couldn't be. Somewhere there was a mistake being made, because f can't be equal to h, and d has to be left by itself. So somewhere we made a mistake. I made a mistake. And the collective class. Did you write something? Can you explain how you determine a difference? Can you explain how we determine the difference? Well, we know that A is, let's see, how do we know that F was not equal to H? Well, F couldn't be equal to H because they had different outputs. So F could never be equal to H. That's for sure. And so if we made an equivalency where we said C equals D, it must have been because F is equal to H. But if F is equal to H, then C can never be equal to D. And in fact, somehow we wrote check mark in here. So I must have missed this X in here. That X is critical because it keeps you from doing that combination. So I'm going to let you guys work through this again, because apparently I flubbed it when I was doing the inspections. Maybe I need to write these matrices a little larger. I'm constrained by the paper. I like to write bigger if I can. Next time I will. Maybe we should just move on if that's all right. So this is number 23, and someone says, uh, 26 and 24. And then Lamb says A equals, this is what Lamb wrote, A equals G equals H, D equals E. No, you wrote D equals F. D equals F, and then E equals B. So this was correct, and this is correct, and this D in here is not, so it's C equals F. Yeah, that makes sense. Let's see, if C is equal to F, then it must be the case that F equals H, but F does not equal H. Can C equal F if F does not equal H? I don't think so. Let me just make sure I wrote this properly. Oh, Lamb writes D equals F. D equals F. Not C. Yeah, that makes more sense. Does D equal F? Yes, if F equals F and if H equals G. Does H equal G? Yes. Yes, that makes sense. So D does equal F. So that actually works. Thank you, Lamb. Now, somebody else writes, can we please do 23? I think that's what we just did. Then they write 26, 26, 24. Let's try and do number 24, since that comes after 23. Because, what the hey, this will go in order, right? And it doesn't look like number 24 is particularly easy, so we might as well try it. Number 24. Homework 11. Consider a sequence detecting finite state machine with a single input X and an output Z. The output is asserted after each 4-bit sequence consists of a binary string of, we're looking for 0, 1, 1, 0, or 1, 0, 1, 0. The machine returns to the reset after each 4-bit sequence. We will assume a melee implementation. Choose the reduced state transition table that belongs to the new finite state machine using row matching to minimize the number of states. Using row matching. Oh boy. This is quite something to be boy, do I hate writing this out. I wonder if it makes sense to rely upon a pre-printed version of the stand by just a second. I'm going to resist the temptation to write out this question because it's going to be fraught with error if I write it, and it's going to take forever. So let's just take a look at the actual question itself and see if we can work with the answer as printed. Because I don't want to write this, right? That's like a, I don't want to write that. Why would anybody want to write that? So let's take a look at the next states and the present state, right? If S13 looks like S14, then any reference to S13 can be rewritten as S14. So I can write that S14 is equivalent to S13, right? Because the next state and the outputs are the same. So what else can I say about this? That this is going to be 13, S13, right? And now I can remove the row because of row matching, and I'll get an equivalent state machine. It's a simplification you don't have to use implication tables for. Let's do that again. Oh, are you not able to see this whole thing? I guess you can see it. So now let's do it again. Does S13 look like S11? Yes, it does. So what I can do is I can say this is equivalent to S11, right? And now, if that's the case, I can remove S13, and anywhere I see S13, I can write S11. And so now I can take a look at S11 and S9. They look the same. So if that's the case, I can remove S11 and write out S9. In fact, now that I think about it, it's equal to S8, right? So if I see S8, 9, 11, 13, or 14, I can just write out S7 because they're equivalent. So if I see S8, like over here, I can write out S7. If I see S9, I can write S7, S10. S10 stays as S10, sorry. Looks like S11 gets turned into S7. S13, don't see that there. S14, that becomes S7. And I see S11 over here, so that becomes S7. So that's pretty good. I like that. And now, it looks like S10 equals S12. So if I see S12 anywhere, I can write out S10. And now, I guess there are two cases of S7 here, right? This one and this one. So now it looks like S6 is equal to S3, right? Because they both say S7. They both have outputs that are the same. So I can remove S6. And anywhere I see S6, I can write S3. Okay. So things are getting pretty simple pretty quick. Let's take a look at S7, S10. This looks the same. So S5 equals S4. So let's take out S5. Anywhere I see S5, I should be able to write S4. And is there anything else that looks like row matching can give us a simplification? I say no, that's pretty good. Let's see if the answer appears. The answer does not appear, and so the correct answer is none of the above, because we should be able to reduce this down to 1, 2, 3, 4, 5, 6, 7 states. And actually S7, yeah, S6 doesn't appear. X6 is a reduction. So there is no correct answer here. None of the above. So the reductions, according to this, should be S7 equals S8 equals S9 equals S11 equals S14. So that's S7. And then the other reduction is S10 equals S12. Is S10 equal S12? Yeah, we got that one already. And the other reduction you'll want to have here is S4 equals S5, and we got that. So S3 is S6, that was in the bottom. So that'll give you your correct answer, but unfortunately that's none of the above in terms of the possible answers. Now it says here, can you do number 26 and 25? This was number 24. Let's do number, I think it says number 26. How are we doing on time? We have time. Let's look at number 26. So number 26 says, given the state transition diagram, find the fully reduced state machine diagram. Note, you are only permitted to use row matching reduction. So that's a Moore machine, because the outputs are only a function of the present state. But the input could be x equals 0 or x equals 1, and the states are labeled A, B, C, D, E, F, G. So the way you do it, and I'll just do it right here on the paper, because I don't know. Can I do this on, do it on here. There, make it neat. Can I get it to fit? I may have to do it. I'll do it on the blank side of this paper. I don't want to redraw this diagram because it looks like a pain to redraw it. So we'll write the present state, and then we'll have the next state, x equals 0 and x equal 1. That'll be the next state. And we'll have the output, so if you're in state A and you get a 0, your next state is going to be B. And if you get a 1, your next state is going to be C. And your output's going to be 0. If you're in state B and you get a 0, your next state's going to be A. And you're getting a 1, you're going to have a C, and your output is 0. For C, if you get a 0, your next state is going to be D. Oops. And if you get a 1, your next state will be C, and your output will be 0. If you're in D, you can get a D for your next state, or an E with an output of 1. And you're in E, your next state is A or F with output 0. When you're in F, next state is going to be B or G, output 0. When you're in G, next state is going to be A or E, output 0. There. Did I do that correctly, everyone? Does it look okay? So now I want to do row reduction. It says here, row matching only. Row matching only. So let's look for BC. Don't see it. Let's look for AC. Don't see it. Let's look for DC. Don't see it. Let's look for DE. Don't see it. Let's look for AF. Don't see it. Let's look for BG. Don't see it. Don't get any reductions here. None at all. And did I make a mistake? Does A equal B? Let's see. Next state for A is going to be B or C. Next state for B is going to be A or C. I could do a, let me just see if I can get this right. If I do an implication chart. B, C, D, E, F, and G. A, B, C, D, E, and F. So A is equal to B if A equals B and C equals C. Oh yes, that's an obvious one, isn't it? So A is equivalent to B. Let's look at things that are not equivalent. A is not equivalent to D. A and B is not equivalent to D. And C is not equivalent to D. And D is not equivalent to E, F, or G. And now I can do is A equivalent to C? Yes, if B is equivalent to D, but it's not. Is A equivalent to E? And the answer is if A is equivalent to B, and it is, and if C is equivalent to F. Maybe it is. So we want to know if C is equivalent to F. A is equivalent to E if C is equivalent to F. C is equivalent to F if B is equivalent to D, and it's not. So this is not equivalent. And C is not equivalent to F. And therefore this is not equivalent. Let's look at C and E just for yaks. Is A equivalent to D? No. So this does get an X. What about A and F? If B is equivalent to B and C is equivalent to G, let's look at C and G. That's AD. AD is not equivalent, so this is not equivalent. A is equivalent to G if A is equivalent to B and C is equivalent to E. C is not equivalent to E, so that goes out. Let's look at B and C. B is equivalent to C if A is equivalent to D, and it's not. Let's look at B and E. B and E. AC, yes. CF, no. BF, we got AB and CG. We don't know about CG. CG. Let's look at CG. C is equivalent to G if A is equivalent to D, and it's not, so that is out, and that is out. How about B and G? B is not equivalent to G. Wait, that's A and A. There's C and E. Oh, that doesn't work. So then how about EF? E is equivalent to F as A is to B, and F is to G. We don't know FG. FG. So let's look at FG. FG if AB and if EF. So it looks like FG, F is equivalent to G, because we have A is equal to B, and if G is equal to E. Do we know about GE? We don't. GE, yes, if A is equal to A, and F is equal to E. So this whole thing is in a cluster. So this is F equals E, and F is equal to G if G equals E. So I can put in check marks here. So now I have E is equivalent to F is equivalent to G, and that simplifies things greatly. So now we're down to, let's see, we've removed, shall we do it here? I guess we can do it here. G and F are both replaced by E. B is replaced by A. And so now we're down to 1, 2, 3, 4 states. Let's see if we got a correct answer here. Yeah, if you just use, you can get a correct answer. However, if you just use row matching, you can't get any of these answers at all. But using the implication chart, you can. And you're only left with A, C, D, and E. And so there is a fully reduced state diagram here, but if you only use row matching, you can't get to it. You have to use an implication chart to get to it. So what we saw, and this is kind of interesting, row matching was not able to give us any reductions at all, but if we use the implication chart, we can get the reductions. So if you gave an answer which you got from an implication chart, it was because you used the implication chart and you didn't use the row matching reduction. So if you're only permitted to use row matching reduction, you cannot get to an optimized answer. And in fact, all of the optimized answers that are shown could only be arrived at if you started using implication charts, not row matching reduction. So it shows row matching reduction over in here as being very productive, but over in here, not productive at all. But what was interesting when we looked at row matching reduction over in here is we were able to quickly get to a reduced set of set states. And we might not be done. We'd still have to use an implication table in order to get a true optimal state machine. So that's kind of interesting. It shows you the power of row matching and also the limitations of row matching. So that was cool. That was a good example. Somebody wrote, I think somebody is looking to get 20, is that 25 I see written? I'm not sure. Yeah.
Just so we can see the answer.
So for this answer, right? If the only thing you do is row matching, then the answer is none of the above, because the only answers that are being presented are answers that you could have obtained through an implication table. So yeah, you can get this if you use an implication table, but if you follow the directions and just do what it says, do row matching, what it does is it illustrates the point that row matching is not a productive way to get an optimization for the state machine. Only an implication chart can discover the equivalencies. And so these two equivalencies that came about from the implication chart, you can't get that from row matching. So row matching was productive only in the case, like over in here, where we saw, man, that row matching was great. But then we went over here and we said, hey, that row matching didn't work at all. So when the chapter shows us row matching and we say, okay, let's try it, if it doesn't do anything, we still have to go and try the implication chart unless it says use row matching reduction. In which case, your only answer has to be none of the above, because none of these answers will come out from using row matching only. Does that? Yeah. Yeah. So it's trying to show the power and the limitation of row matching. Now, somebody said, can we do 26? Wait, didn't we just do that? That was 25. Okay, so let's do 26. 26. Let's do 26. Let's see if I can get the picture on my computer. I can't find my mouse. What happened to the mouse? Shoot. I don't know what happened to our mouse. I think I've crashed my computer. You guys can still hear me though, right? Oh, good. Okay. So I'm just going to go to the paper copy then. Let's see. Number 26. 4. 25. Here's 26. Oh no, it's so small. It's very tiny. Let me see if I can get an exploded version of this. Here's a slightly larger version. It's not as big as I would have liked, but maybe I can get something from it. Choose a fully reduced state diagram given the above state diagram. So let's try this. It's A, B, C, D, E, F, G. I'm going to write it over here. Present state, next state, output. A, B, C, D. There's no H. Next state. For x equals 0, x equals 1, and then output. Yeah, it's looking a little too jammed up to get done properly. I'm going to have to get a separate piece of paper for this one. This is better. Let's make it nice. So we'll do this. Present state, x equals 0, x equals 1, output. And that'll be the next state. There. So when A is equal to 0, the next state is A or C. B. Next state is going to be D or B. C. Next state is going to be D or B. D. Next state is going to be B or C. E. Next state is going to be E or F. F. Next state is going to be G or B. G. Next state is going to be B or F. Now that I have encoded the diagram properly, hopefully, I can work off the graph paper. Just out of curiosity, I wondered if I could get a reduction using row matching. I don't see AC anywhere. The outputs here are different from everything else. DB looks different, BC looks different, EF looks different, GB looks different, BF looks different. So I can't do row matching here. It doesn't help me at all. Did I just do that wrong? Okay, what's wrong with this? A, B, C, D, E, F, G. B, C, D, E, F, G. A, B, C, D, E, F. Something is wrong. Okay. Somehow there's a scribble in here. Sorry about that. So now, B can be different from C, D, E, F, and G. But there are no other trivial reductions from outputs being different. So now, let's look at A and B. A and B are the same if A equals D. I don't know about AD, so let's go and look at AD. AD is the same if A equals B. So A equals B if A equals D, and A equals D if A equals B. So that's in this circle, right? A equals B if A equals, let's see, A equals B if A equals D. What about C and B? Does C equal B? For some reason, we're not seeing the BC working. So A cannot equal B since B does not equal C. So A can't equal B. In fact, if you think about it, C can't equal D for the same reason. And D cannot equal F for the same reason. In fact, the way you could do this is kind of interesting. If you see combinations of B and G, F and G, for example, they can't be equal. You might look for combinations of B and F. For example, E and F couldn't be equal. It's sort of an interesting way to work backwards. I don't normally do this, but let's do it just for fun. We know that BE cannot be equal, so if we see combinations of B and E, for example, DE, we know BD cannot be equal, so if we see BD anywhere, such as BD and also, where else? CG, that can't be equal because BD. And then BC cannot be equal, so if we see combinations of BC, such as AB, which we know is not equal, CD, which we also have an x on. So that's kind of neat. We got rid of a whole bunch of these things just by looking at what we knew was not equal. And in fact, since AB is not equal, then we know AG can't be equal because AG requires AB. So you're working backwards now from those things that you're discovering, which is kind of interesting. Another way to do it, I suppose. If AG is not equal, then AF can't be equal. If AF is not equal, then don't get anything else out of it. And with GF, you can work backwards. It's kind of interesting. So let's go AC and see what we got. Is AD got anything for us? Maybe. How about BC? No. So AC is no good. What about AD? We got AB. That's no good. What about AE? AE is good if A is equal to E, and is good if C is equal to F. So does C equal F? Let's see. Let's look at CE. CE is okay if D equals E. D doesn't equal E. So then what about CF? CF is okay if D equals G. So CF is good if D equals G and if B equals B. Does D equal G? D equals G if B equals B and if C equals F. So now we're getting somewhere. D is equivalent to, let's see, G, so that's good. C is equivalent to F, so that's good. And what about GE? Well, G is equivalent to E if B equals E, but it doesn't. And so this is what I got. And now that says to me, everywhere I see F, oops, I write in a C. Everywhere I see G, I write in a D. And now A, B, C, D, E are all I have left. That's pretty cool. Let's see how that compares with my answer key. So this was question number 26, I think. This is what we started with. We were saying D equals G. So this gets erased. And, or you can say this gets erased. And this is kept because this becomes DG. And then CF. I don't see an F in here. Wait a minute. Oh, I'm looking at the answer key instead of the original. So here is here's what I'm trying to get at. So we got D equals G. So these two should be equal. That means this one will get removed and replaced with this one over here. Also, C is equal to F. So that means this one will get removed and replaced with that one over there. So by the time we're done, we should see something with only B, A, B, C, D, and E. And so I don't see those, and so what I get is none of the above. So that's kind of neat. Another none of the above question. Had to do a lot of work to find that one. Now somebody said, can you please do number 26? I think that covers everything people asked about, and we've gone on for a bit of a time here, so that's good. I still can't seem to find my my mouse. My cursor has disappeared. Oh, here it is. It's on another screen. I just want to scroll down and make sure you have everything. Are there any other questions that you have for me? Well, seeing that there aren't, I thank you all. I've recorded this session, such as it is, and I will post it. Yes. Oh, for homework 10. I see. Does anybody else need an extension on that deadline? No, it doesn't sound like it. But you know what I'll do is I'll make it due tonight, and that way people can have a chance to look at it again in case they didn't submit it twice. So, all right, that's great. Well, thank you all for tuning in. I hope this extra help session was of some use to you, and if you have any other questions for me, please feel free to shoot me an email. Thanks a bunch. Stay safe and enjoy your holiday. Bye-bye.